Today, I want to do a fun proof from this textbook right here. And we're going to be proving that with all the people in the US, right, two of them will have the same weight of each other when rounded to the nearest millionth of a pound. And how are we going to do this? Well, we're going to do this using the pigeonhole property. Now, what is the pigeonhole property? Well, just a little recap. If we have 8 boxes and 9 objects, right, and you put an object into each box, we can guarantee that one of the boxes will have 2 objects in it. Right? We can guarantee that. We can say that for certain. That's the pigeonhole property, and we're going to use that to prove this. So the first thing that we want to do when proving this is define our objects and our boxes, right? So our objects will be people, okay? I know that sounds bad to say, but that will be our objects, okay? And then our boxes will be weights. All right? So, now that we have that, we need to set a range on our boxes and our people, right? Basically, for people, we need to determine how many people are we working with, and for weights, what is the range of our weights, right? So basically, how many boxes do we need? So how many people are we working with? Well, how many people are there in the US? There are 330 million people in the US, right? But 330 million people, there's a very, very wide range of weights in there, all right? We could go from 1,000 to 0 pounds, 0 to 1,000 pounds, right? We just don't know. So basically what we want to do is we are going to take, okay, well, how many people are over 300 pounds, right? And you can Google that, and it's about 0.1% of the US population, or about 330,000 people. And we're going to subtract that from this. So 330,000 people, right? So when we subtract this, what do we end up with? We end up, this equals, here I have it on my computer here, 3. No, sorry. So we end up with this number here, right? So now we know exactly how many people are we working with, and what is the weight range? Well, the weight range, like we just said, is going to be from 0 to 300, because we just got rid of all the people from our population who are over 300 pounds. So now we need to determine how many boxes are there, because it's great we know that's 0 to 300, but we're not working with 300 boxes. We're working with a lot more than 300 boxes, because we're rounding to the nearest millionth. So we want every single box to represent a weight possibility. So our first box should be like 0. This should be our first box, and then our next box would be this, and our next box would be that. We want every single box to represent our weight range, right? Or next, the following weight. That's what we want every single box to represent. So how do we get how many boxes we're working with? We take this 300 number, right? Our maximum weight, and we're going to multiply it by 1,000,000, because we're rounding to the nearest millionth. So we're going to take the highest possible weight and multiply it by what we're rounding to, right? And this just gives us 300 million. Right? So now we have the amount of people we're working with, and we have the amount of boxes we're working with. Now, all these numbers coming after the 300 million, we don't need to pay attention to exactly what those numbers are, but the most important thing that we have to note here is that this number is greater than this number plus 1, right? Because that's what's very important for the pigeonhole. We need the amount of boxes to be, let's say we're working with n objects, we need n minus 1 boxes, right? Or if we're working with a better way to rephrase that, if we're working with n boxes, we need n plus 1 objects, right? So this is greater than n plus 1, so it still works fine as well. So now we can say through the pigeonhole property that we can guarantee that there will be 2 people in the US who have the same weight rounded to the nearest millionth. Thank you for watching.